paper called MODA, mapping one's audio-driven portrait animation with dual attentions, published in ICCV 2023. So the purpose of this paper is the purpose of building this model is to synthesize high-fidelity portrait videos linked to provided audio inputs and the given portrait. Aims to create natural facial animations capturing various movements, lip sync, head pose, and eye blinking. Addresses issue of unnatural results, lack of correlation between facial movements and the audio. And they propose this solution, unified system for multi-person, diverse, and high-fidelity talking portrait generation. Their proposed model consists of 3 stages. First, there is mapping one's network with dual attention to decode the accurate mouse movements and diverse modalities from given audio. Then we have facial composite network. It produces dense, detailed face landmarks based on the landmarks and the audio, encoded audio. Then we have temporal guide renderer to synthesize stable videos. Advantages, the extensive evaluations show they are like state of the art compared to the current methods. Enhanced correlation between audio, facial modes for heightened realism. Okay, the point of this task is given input audio and a portrait of a person. Talking portrait animation is to synthesize video frames of the person, and the expressions are synchronized with the audio signals. This has very broad applications in industry: digital avatars, gaming, telepresence, VR, video production, and eventually scamming and fake news. The challenge of this task is 3D face reconstruction and GAN-based methods estimates intermediate representations. And this methods, such sparse representations usually lost facial details, and we get very smooth results. And another challenge is humans are extremely sensitive to the facial expressions, and they can easily identify any artifacts in the facial expressions or lip expressions. Contributions of this paper. They achieve cutting-edge performance. They generate realistic multimodal portrait videos. And the main innovation is mapping one's dual attention network, MODA. Then it has 3 stages: transformer-based dual attention network, facial composite network, and temporal guide renderer for high-quality, stable video synthesis. The related work to this paper, technologies such as flow learning and memory banks overlook crucial elements like head pose, torso motion, and eye blinking. And use of nerve and neural radiance fields and diffusion-based methods, and they fail to become applicable because of the limitations due to extensive sampling steps. And there are also works, GAN-based works, utilization of sparse representation like 2D landmarks and 3D shapes. There are other works, the GAN-based work, like in intermediate, they predict 2D landmarks of the 3D face shapes or facial expressions, and that sparse representation loses much information. There are transformer and vision-based techniques. And in image to image translation, if we render the videos in the end single frame, we get artifacts in the background. Background want to be stable, and they propose to render the no, to render the result conditional on the before result, like autoregressively, so we don't get such artifacts in the background. The overview of this model. First, we have MODA. We give audio and the subject, and here we extract key points, facial key points using another network, like pre-trained another network. Then we have a MODA, dual attention network, and it produces head pose, mouse, eye, and torso. And we have FACONet, a facial composer network. It is vanilla GAN to enhance the key points based on mouse, eyes, and after that we transpose our coordinates, our 3D landmarks into camera space. Then we render output frames here. So given that the length audio sequence with audio sampling rate R, the model maps it into corresponding video clip V with FFPS, where K is this formula. Since the data dimension of V is much larger than A, V is video and A is just audio, so V is much larger in data dimension. The model produces V progressively and introduces intermediate variables, intermediate representation R. In this model, they choose R as mouse points, eye points, facial points, head pose, and torso points. Each are 3D points to represent mouse, eyes, facial, and for head pose they use Euclidean angle for rotation and head transpose in Euclidean space. Then they also use torso points, like shoulders, to describe shoulders, 9 points in each side. Then the whole process is first we encode our audio into representation R, then we produce video. This is the first stage of the network. We have audio wave and subject landmarks produced from the subject portrait. And audio encoder is a simple wave to vector, like a previous method. Then we use embedding. Embedding is just fully connected network. Then we have embedding of the subject landmarks. Then we add them element wise, and we have representation T by D, D by T. D is the data dimension, and T is the time frames. T is the frames. Then we feed into the dual attention network. We have two attention networks: specific attention and multimodal attention. Specific attention captures the temporally aligned attention between S and SA. Here we see between S and SA. Its formulations is like this. It is first does the self attention in S with positional encoding. Then it uses or simple attention between S and SA. They also use this to this MA blocks the future future frames to attend the past frames. Yeah. Then we have multimodal attention here. It learns probabilistic mapping between audio features and portrait motions. It's based on variational autoencoders, but we use encoder and decoder are transformers, so it is transformer variational encoder. Encoder produces means and the variations for the probability distribution. Then in decoder, we sample from that distribution and decode. So this sampling process gives variety to our model. In the next stage, we have facial composer network, given subject information S, generated mouse points and eye points, aims to incorporate refined facial landmarks. We already have subject landmarks, and we want to refine it using predicted mouse points and eye points. It is based on vanilla GAN architecture. Discriminator network this FACONet tries to a full discriminator, while the discriminator is trained to distinguish generated facial points from ground truths. After composition, the facial landmarks are transformed to camera coordinate via head pose, angles, and the coordinates. Transformed facial landmarks and torso points are projected into image coordinate. After transforming to camera coordinate, we transpose them into image coordinate. Then we have the last stage of our network to render the videos. They used a UNet-like renderer with positional encoding. This is a formulation of positional encoding. This positional encoding gives us stable rendering of videos. If they don't use positional encoding, model can produce artifacts in the background. But if they added the positional encoding, it stabilizes the video between frames, so it gets rid of the artifacts in the background and unwanted behavior. Yeah. Then in the experiments, they use HDTF and LSP datasets. That datasets contains videos, high resolution videos with audio track. Facial landmarks in the beginning of the network are generated using media pipe. This is a whole pre-processing method. They use media pipe to predict face mesh and head pose estimator, then semantic parsing to produce torso point extraction. They incorporate torso points with face mesh and head pose, all of them, to produce condition image to give the MODA network. To compare with the previous methods, they used several metrics, mouse landmark distance and velocity of mouse landmark distance, to compare how good the model is performing rendering the lip motion, mouse motion, lip synchronization. and they use SyncNet to measure the audio-video synchronization and the overall to assess the overall image quality. Natural Image Quality Evaluator, NIQE. This is quantitative comparison using these metrics. These are the previous methods, and these are the results from this paper. And according to them, they achieved state of the art in many of the metrics, NIQA, LMD, LMDV, except the synchronization. In synchronization, they couldn't beat previous methods. They also conducted quantitative, this should be qualitative evaluation. This is wrong. They conduct qualitative evaluation. They use 20 attendees on 30 videos generated by this model and other methods. Drawing audio selects from different languages, and each participant is asked to select best generate talking portrait videos based on 3 major aspects: lip synchronization, naturalness of movements, and overall video quality. And this is the result of qualitative evaluation compared to Make It Talk, Wave to Lips, and SAT-Talker networks. As we can see, their network is superior in even lower resolution and high resolution based on qualitative evaluation. Thank you. This was all from me.